Howdy. This video is on wave nature of matter and Heisenberg's uncertainty principle. Wave-particle duality of really small things and Heisenberg's uncertainty principle are related, are indicative of the composition of energy and matter. Wave-particle duality and Heisenberg's uncertainty principle indicate how different things behave at the submicroscopic level. And so after watching this video, you should be able to describe how light, electrons, and atoms do not behave like apples. You should be able to calculate the wavelength of a moving object. You should be able to calculate the minimum uncertainty in position or momentum given the other. And so you can characterize things that are composed of waves in terms of the frequency. Frequency is the number of wavelengths that passed in 1 second. And so we're plotting the x-axis time. And so if we look at the red one, we have 1 wave, 2 waves, 3 waves, and so that would give us 3 wavelengths passed in 1 second. We'd say that was 3 hertz. Hz stands for hertz. A hertz is 1 over a second. If we look at the blue, we have 1, 2, 3, 4, 5, 6, and again that would correspond to hertz. And so it's the number of wavelengths that pass in 1 second. Wavelength is the length of one wave in terms of distance. And so in the previous slide we had plotted as a function of time. Here we plot as a function of distance. And so we have a distance of 1 centimeter going from top to top, and so that would be the wavelength. We could also have gone from bottom to bottom. That would be 1 wavelength, 1 centimeter. Now the for electromagnetic radiation, frequency is equal to the speed of light divided by the wavelength. And so again, we use nu for frequency, speed of light we symbolize with c, wavelength we use lambda. And so the speed of light is 3 times 10 to the 8th meters per second. That's the speed of light in a vacuum. It is a constant of the universe, divided by our wavelength of 1 centimeter, which is equal to 1 times 10 minus 2 meters. The meters cancel. We're left with 1 over a second, which again corresponds to hertz. And so that would give us 3 times 10 to the 10th hertz. So again, frequency is just equal to speed of light divided by the wavelength. Now if we look here, we have half the wavelength. It's 0.5 centimeters, which is equal to 0.5 times 10 minus 2 meters. And again, meters cancel. We're left with 1 over a second, which is a hertz. And you cut the wavelength in half, and that actually doubles the frequency. And so the shorter the wavelength, the higher the frequency. Now we saw previously that the energy of a photon is equal to Planck's constant times frequency. We just saw that frequency equals speed of light over wavelength. And so if we plug that in for frequency, we get energy of a single photon is equal to Planck's constant times speed of light divided by the wavelength. And so Planck's constant 6.626 times 10 minus 34th joules per second times our speed of light, 3 times 10 to the 8th meters per second divided by the wavelength, which again 1 centimeter is 1 times 10 minus 2 meters. Meters cancel meters, seconds cancel seconds. We're left with joules, and we get 2 times 10 to the minus 23rd joules. If we look at 0.5 centimeters, we would get 4 times 10 to the minus 23rd. And so the shorter the wavelength, the higher the energy. The longer the wavelength, the lower the energy. Wavelength and energy are inversely proportional, just like frequency and wavelength are inversely proportional. And so electromagnetic radiation is characterized by wave properties, wavelength, and frequency, characterized by particle properties of energy. And so again, please make sure you know that wavelength times frequency is speed of light. Energy is equal to Planck's constant times frequency, which corresponds to energy equals Planck's constant times speed of light divided by the wavelength. Now, given any one of those 3 parameters, you should be able to determine the other 2. So this problem asks you, how much energy does a mole of photons with a frequency of 1.30 kilohertz have? And so we've seen that the energy for a single photon is equal to Planck's constant times frequency. Now if we look at the worksheet, on that first page you have a periodic table. You also got constants. You're always given this first page on all your exams. And so here's your Planck's constant, 6.66 times 10 to the minus 34th joule seconds. And then we have 1.30 kilohertz. Now if we go back to the worksheet on the second page, it gives you SI prefixes. Now notice that this will never ever be given on the exam. You're expected to have these memorized. And so K is kilo, it's 1,000. And so if I go back here, and instead of writing K, I just go times 10 to the 3. Now remember that a hertz is inverse second, so I'll put that there. Now if I multiply that out, and so if you're doing times 10 to the something, please use your EE button. So we got 6.626 EE 34th negative. So that's 6.626 times 10 to the minus 34th. So again, if you have times 10 to the something, use the EE button. Multiply times 1.3 EE3. And that gives me 8.6 times 10 minus 31. That's for a single photon. We're asked about a mole of photons. So we have to take that 8.61, times 10 minus 31 joules. And we have to multiply it by Avogadro's number, 6.022 times 10 to the 23rd. And again, if we look at our worksheet, we'll see that Avogadro's number is right there, 6.022 times 10 to the 23rd. Okay, and so we go back. And we just multiply this times 6.022 EE23, and I get that. And so if I count the number of dots, well, that's going to be a decimal point over 1, 2, 3, 4, 5, 6, 7. And so that gives me 5.19 times 10 to the minus 7 joules. And that's for a mole of photons. And so here we're given frequency and asked for the energy of a mole of photons. You could also be given, this is for a single photon, and we're asked about wavelength. And so if you remember, frequency times wavelength equals speed of light. And so frequency is equal to speed of light over wavelength. We saw in the previous problem that for a single photon, energy equals Planck's constant times frequency. Now if we plug in c over lambda for frequency, we get hc over lambda. And so Planck's constant is 6.626 times 10 to the minus 34th joule second. Again, it's on the front page of the worksheet. Speed of light is 3 times 10 to the 8th meters per second. That's also on the front page of the worksheet. And our lambda is given as 1.7 kilometer, and so the K stands for 10 to the third. So I just write down that for K, and then I have meter. And so meter will cancel meter, second will cancel second. I'll be left with a joule. And that's my calculator. So we got, let's clear this, 6.626 times 10 to the minus 34th. I use my EE button, times 3 to the 8th. Sorry, 3 times 3 times 10 to the 8th equals, divided by 1.7 EE3, and that gives me 1.17 times 10 minus 28. And that would be joules. Now again, because they asked for a single photon, we don't have to multiply by Avogadro's number. We can look at one more. And so here we're asked, what is the wavelength of electromagnetic radiation with a frequency of that? And so for electromagnetic radiation, we know that wavelength times frequency equals speed of light. We're looking for the wavelength. Oops, sorry. We're looking for the wavelength. And so that's equal to speed of light over frequency. And speed of light is 3.0 times 10 to the 8th meters per second. Now our frequency is 1.70 times, now the M is mega, and that's times 10 to the 6. And hertz again is inverse seconds. And so inverse seconds cancels inverse seconds. And we need the calculator. Okay. And so we clear it. And so we got 3 times 10 to the 8th divided by 1.7 EE to the 6. And that gives me 176. And that would just be meters. And so we had just derived equals hc over lambda, this equation here. Equals mc squared is Einstein's famous equation from relativity. And so if we take the mc squared and set it equal to hc over lambda, we get that. Now if we divide by c, we get this. And now if we divide both sides by mc, multiply both sides by lambda, we get the wavelength is equal to Planck's constant divided by mass and speed. Now this is an interesting equation. De Broglie actually hypothesized that for matter they should have a wavelength equal to Planck's constant divided by mass and speed. It's kind of interesting. De Broglie's dissertation, PhD dissertation, I think was something like on order of 9 pages. His committee was kind of dumbfounded on whether or not he deserved his PhD, so they sent it to Einstein, and Einstein said, yeah, sure, of course, give it to him. And so wave properties are important. We've seen at the atomic level, really small stuff has wave properties. And so please remember, for electromagnetic radiation, we have this set of equations. For matter, we have this set of equations. Now, if you're asked about wavelength, you have to make sure you know if you're talking about matter or if you're talking about electromagnetic radiation.
Electrons have wave properties. If we shoot a beam of electrons through thin metal foil, the atoms of the foil cause the waves to interfere with each other. The interference, or diffraction pattern, can be recorded on photographic film as a series of concentric circles.
And so a diffraction pattern indicates wave-like properties, and so electrons have wave-like properties. And then again, we can calculate the wavelength for the electron by Planck's constant mass over speed. And so an electron with a speed of 1.9 times 10 to the 8th centimeters per second would actually have a wavelength of 0.388 nanometers. Now, that's correspond to 3.9 angstroms. And so the wavelength is getting down to the size of an atom. And so that's why you can actually use electron diffraction to look at the structures of solids. Now, in terms of microscopy, light microscopy, the resolution is limited by the wavelength. And so you can resolve things down to about 200 nanometers. Nanometer is 10 to the minus 9th meters. With the electron microscope, you can actually get smaller wavelength, which corresponds to higher resolution. Now, it's kind of confusing. When I say higher resolution, I mean smaller number. You're able to resolve more things. And so because the wavelength of electron can be much smaller than that of light, an electron microscope can resolve more things than a light microscope can. And so for higher resolution, you want the smallest wavelength possible. And so that would correspond to a highest speed possible. So the faster electrons, the higher the resolution. And so in an electron microscope, you're just basically using the electrons instead of using light. And so this gives you the resolution. And so a light microscope can get down to something on the order of 10 to the minus 6 meters. Electron microscope can get below 10 to the minus 9th meters. And so you're actually starting to able to resolve atoms. And so you could be asked a question like, if you want to resolve two atoms 1 nanometer apart using electron microscope, how fast do the electrons have to move? Now, if we assume the resolution microscope is equal to half the wavelength, then the wavelength would be equal to 2 times the resolution. And so we said we want a resolution of 1 nanometer, and so 2 times 1 nanometer gives us 2 nanometers. Now we saw the Broglie wavelength is equal to this, so we solve for speed. So speed is equal to Planck's constant divided by mass and lambda. And so Planck's constant is 6.626 times 10 minus 3/4 joule seconds. The mass of electron, and then our wavelength, we just calculate as 2 times 10 minus 9 meters. Now, it doesn't look like our units are going to cancel. Remember, the joule is equal to kilogram meter squared per second squared. And so if we plug in that for a joule, second cancels with one of those seconds. Kilogram cancels with kilogram. One of these meters cancels with one of those meters, and we're left with meters per second. Now, if we plug in the numbers and do the math, we get a speed of 3.6 times 10 to the 5th meters per second. And so if we can accelerate the electrons so they're moving at 3.6 times 10 to the 5th meters per second, we should actually be able to resolve two atoms that are 1 nanometer apart. Really pretty cool. Here's some SEM. So SEM stands for scanning electron microscopy. Here we have a white blood cell, platelet, red blood cell, flu virus, Ebola virus, hafnium oxide nanocrystal. And so this line corresponds to 2 nanometer. And so you are starting to resolve atoms. Magnetite, this line corresponds to 5 nanometers. And again, the white dots correspond to specific atoms. And so we're asked about how fast an electron is traveling if its wavelength is this. And so we're going to have a relationship between speed and wavelength. And so we had the de Broglie wavelength is equal to Planck's constant divided by the mass over speed. Now we're asked for speed, and so if we multiply both sides by speed, divide both sides by lambda, we get the speed is equal to Planck's constant mass wavelength. And so Planck's constant, it's given on the front page of the worksheet as 6.626 times 10 to the minus 34th joule seconds. Now for the mass, we're looking for the mass of an electron. And so we can also find that at the first page, the front of the worksheet. So electron mass is 9.11 times 10 to the minus 31 kilojoules. Now our wavelength is 1.8 kilometer, and so that's 1.8 times 10 to the 3. Remember, K is times 10 to the 3 meter. And so the units are a little confusing. Remember, a joule is equal to a kilogram meter squared per second squared. And so this meter will cancel with one of those meters. This kilogram will cancel with that kilogram. And that second will cancel with one of those seconds. And so we'll be left with meters per second, which is in terms of speed. And so let's clear us. So 6.626 EE 34th negative divided by 9.11 EE 31 negative. Divide that by 1.8 EE3. And so count the number of places we have to move the decimal point. 1, 2, 3, 4, 5, 6, 7. And so that gives us 4.04 times 10 to the minus 7. And that would be meters per second. So the maximum resolution of electron microscope is equal to 1/2 the wavelength. And so resolution is equal to 1/2 of lambda. And so that tells us that the wavelength is equal to 2 times the resolution. So how fast does the electron have to travel for a microscope to have a resolution of 1.4 nanometer? And so 2 times 1.4 nanometer means our lambda, our wavelength, is going to be 2.8 nanometer. And so if we go back to the Broglie equation, so wavelength is equal to h mass over speed. And so we have to solve for speed. And so speed is equal to Planck's constant, mass over wavelength. So Planck's constant, 6.626 times 10 to the minus 34th joule seconds. Now the mass of electron is 9. Well, let's take a look. So remember, constants are always on that front page. You get the front page of the worksheet for all your exams. So mass of electron is 9.11 times 10 to the minus 31. Kilogram. And our lambda, we had 2.8. And again, nano is 10 times 10 to the minus 9 meters. And so we need our calculator. And so let's clear that. So 6.626, 34th negative. Again, when we have times 10 to something, we use the EE buttons a lot easier. Divided by 9.11 times 10 minus 31. Oops, crap. Let's do this again. 6.626 EE 34 negative divided by 9.11 EE 31 negative. divided by 2.8 EE9 negative. And so I get 2.6 times 10 to the 1, 2, 3, 4, 5. 2.6 times 10 to the 5. Now again, remember, a joule is equal to kilogram meter squared per second squared. And so that second cancels with one of those. That meter cancels with one of those. And the kilogram cancels the kilogram. And so we're left with meters per second. And the last equation we could look at, or question we could look at, what is the speed in meters per second of electromagnetic radiation with a wavelength of 1.8 kilometers? Now this one's kind of a tricky question. Electromagnetic radiation, light is just electromagnetic radiation, and so the speed of light in a vacuum is constant, and so it's just 3 times 10 to the 8th. And so be careful, know that if you're being asked about matter or if you're asked about electromagnetic radiation, the equations are different. Now, Heisenberg's uncertainty principle also is related to wave-particle duality, and what it says is that there are pairs of parameters that cannot be known with complete certainty at the same time. And so notice that it's not measured, but known with complete certainty at the same time. And so one example of Heisenberg's uncertainty principle is position and momentum along the same axis. And so the uncertainty in position times uncertainty momentum is always greater than or equal to Planck's constant divided by 4 pi. Now this is actually fairly important if you want to think about electrons and atoms, and it illustrates why electrons cannot orbit nuclei in well-defined patterns, because we cannot know with certainty the position and the momentum.
Heisenberg's principle indeed is very, very non-intuitive. Frankly speaking, I'd call it bizarre. But you can see it at work. Suppose I have a laser beam here, and I use laser beam because that's right, but I could use any other light for that matter. And I make here an opening, a slit, a vertical slit. And here goes the laser beam right through the slit. Light goes on, and here I project this onto this wall or screen, projection screen, and what do I see? Well, you see exactly what you predict. You see here this laser spot from this beam. But now I'm going to make this vertical slit narrower and narrower and narrower. What now are you going to see? Well, you're going to see exactly what you predict. You're going to cut off the edges of the circle, and the spot gets narrower and narrower and narrower. But now you come to the point that this narrow slit, say, is only 1/100th of an inch wide. And now Heisenberg's principle comes in. Because now you know so precisely in the horizontal direction where the light is, that as it emerges from this slit, the direction of the light is no longer determined according to Heisenberg's principle. And so now what you're going to see, it's going to spread out in the horizontal plane, and therefore what you're going to see on this projection screen is going to get wider. Extremely non-intuitive. Because what am I doing? I'm making the slit narrower and narrower and narrower and narrower. And what do you see ultimately? That the beam horizontally becomes wider and wider and wider and wider and wider and wider and wider. Now that is very non-intuitive, but it's the way the world works.
So really cool. As the slit gets really, really narrow, the uncertainty in the position in that axis gets really, really small. Also, the uncertainty in momentum increases, and that's what causes the light to spread out. And so hopefully you can describe how light, electrons, atoms do not behave like apples. You should be able to calculate the wavelength of a moving object, or calculating how fast something has to move to get to a certain wavelength. You should be able to calculate the minimum uncertainty in positional momentum given the other one. I hope that helped.